3 interstellar messengers, all on different roads, yet their routes fit together like threads in a pattern we were never meant to notice. Oumuamua, Borisov, and now 3I-ATLAS. Each came from the stars, followed a path too deliberate to dismiss, and left without stopping by. They moved like survey drones, sampling atmospheres, recording chemistry, transmitting data back to somewhere we can't see. 3 samples, 3 reports, each brushing past Mars, Venus, Jupiter, but ignoring Earth. Almost as if, when it comes to us, our data is filed, our chemistry logged, the work already done. And 3I-ATLAS hasn't broken that pattern, it perfected it. Stay until the end, because tonight we connect these paths, and what we uncover is a chilling truth no one is ready for. If these mysteries have you hooked the way they have me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The quiet geometry of 3I-ATLAS. There are moments in history when the universe hands us something we weren't ready for. July 1st, 2025 was one of those moments. A telescope array in Chile, part of the asteroid terrestrial impact last alert system, caught something moving through the darkness, something that didn't belong. They called it 3I-ATLAS, the third interstellar object we've ever detected, the third visitor from beyond our solar neighbourhood. And when astronomers traced its path backward and forward through time, they found something that should make your skin crawl. The trajectory isn't random, it's precise. Most objects that wander into our solar system follow predictable patterns, ellipses carved by gravity's patient hand over billions of years. They orbit, they return, they behave. But 3I-ATLAS doesn't orbit anything. Its path is hyperbolic, which means it came from somewhere else entirely, and it's going back out into the galactic night. That part we expected. What we didn't expect was the route it chose to take on its way through. Picture this. An object enters our solar system moving at roughly 60 kilometers per second. That's about 37 miles every single second. It's coming in from the direction of Sagittarius, from the deep space between stars where light takes years to cross the emptiness. And as it approaches, it begins to thread through our planetary system with surgical precision. On October 3rd, 2025, it passes Mars at a distance of 0.19 astronomical units. That's close, uncomfortably close for something moving that fast. Then on October 29th or 30th, depending on final calculations, it reaches perihelion, the closest point to our Sun, at about 1.36 to 1.4 astronomical units. That places it squarely between Earth and Mars, but it doesn't stop there. November 3rd, 2025, it passes Venus at roughly 0.65 astronomical units. And then, months later, on March 16th, 2026, it sweeps past Jupiter at 0.35 astronomical units. Mars, Venus, Jupiter, 3 worlds, 3 very specific worlds. And here's what should bother you. Earth isn't on that list. Think about what those 3 worlds represent. Mars is the dry world, the dead world, a place where water once flowed and life might have sparked before the atmosphere bled into space. Venus is the toxic world, the burned world, where a runaway greenhouse effect turned a potentially habitable planet into a pressure cooker with clouds of sulfuric acid. And Jupiter, with its system of moons, Europa and Ganymede and Callisto, represents the icy ocean worlds, places where liquid water hides beneath frozen shells, and life might still be waiting in the dark. It's a sequence, a progression, from dry to toxic to frozen wet, from past habitability to failed habitability to potential habitability. It's as if someone drew a line through the evolutionary stages of planetary environments and said, sample these, measure these, catalogue these, and Earth? Earth is skipped entirely. Now you might be thinking, it's just a coincidence. Space is big and objects move through it without purpose or design. Random trajectories are just that, random. Sometimes they happen to line up in ways that look meaningful to pattern-seeking human brains, except there's more. The orbit of 3I-ATLAS is retrograde, meaning it's moving in the opposite direction to most objects in our solar system. And while its inclination is only about 5 degrees off the ecliptic, the plane where most planets orbit, its direction is roughly 175 degrees. It's moving almost perfectly counter to the flow, almost perfectly aligned with the planetary plane itself. That maximizes its chances of intersecting with planetary orbits. Most interstellar objects come in at random angles. They plunge through the solar system at wild inclinations, missing everything important, and shoot back out into the void. But not this one. This one came in flat, came in aligned, came in where the worlds are. Then there's the chemistry. When astronomers pointed the James Webb Space Telescope at 3I-ATLAS and analysed the light passing through its coma, the cloud of gas and dust surrounding it, they found something strange. The coma is dominated by carbon dioxide, not water, not the mix of volatiles we see in most comets. Carbon dioxide with a ratio to water of about 8:1. That's among the highest ever observed in a comet. It's backwards. It's wrong. Or rather, it's unusual enough that it demands explanation. Carbon dioxide is what Mars and Venus have in abundance. Mars's thin atmosphere is 95% CO2. Venus's crushing atmosphere is 96.5% CO2. And here comes an interstellar visitor, rich in the very substance that defines those two worlds, passing both of them in sequence. If it were here for Earth, you'd expect water. You'd expect organic compounds that mirror our oceans and our atmosphere. But it isn't here for Earth. It's here for something else, and that's the part that should keep you awake. Scientists are still calling it a comet. They're still treating it as a natural object, a chunk of ice and rock that formed around another star billions of years ago and got kicked out into interstellar space by gravitational interactions. That's the safe interpretation, the reasonable interpretation. But when you zoom out and look at the geometry, when you see how perfectly it threads through the habitable zone candidates, when you notice that it's rich in the exact volatile that two of those worlds breathe, you start to wonder, what if this isn't random? What if this path was chosen? Part 2. Trajectory. Deep dive. From discovery to the planetary waypoints. The discovery itself was almost mundane. ATLAS, the same system that watches for asteroids that might threaten Earth, caught a moving dot on July 1st, 2025. Just another piece of cosmic debris, or so it seemed at first. But when astronomers started pulling archival images, checking older observations, they realised this object had been in the sky for weeks. They'd missed it. We'd all missed it. And once they plotted its trajectory forward and backward through time, the implications started to sink in. Hyperbolic orbit. That's the technical term for an object that isn't bound to the sun's gravity. It came from outside and it's leaving. The math is unambiguous. When you calculate the orbital energy and it comes out positive, you know you're dealing with something that will never return. Oumuamua was like this. Borisov was like this. And now 3I-ATLAS joins that exclusive club of confirmed interstellar visitors. The incoming velocity was pegged at around 60 kilometers per second relative to the Sun. That's fast, but not impossibly fast. It's consistent with an object that's been drifting through the galaxy for millions or billions of years, picking up speed from the rotation of the Milky Way itself and the random gravitational tugs of passing stars. The direction it came from, somewhere in Sagittarius, doesn't point to any particular star system we know of. But then again, stars move. By the time 3I-ATLAS left its home system, assuming it ever had one, that star could be anywhere. What makes this object different isn't just that it's interstellar, it's the inclination. 5 degrees off the ecliptic. That's almost nothing. Most interstellar objects should come in at random angles because interstellar space has no preferred orientation. You'd expect inclinations spread evenly across all possibilities. But 3I-ATLAS is nearly coplanar with the planets, and that retrograde direction, 175 degrees, means it's threading through the system in the plane where all the action is. Imagine throwing a dart at a spinning disk from across the room and hitting it edge-on. That's what a random interstellar object would have to do to stay in the plane. But 3I-ATLAS did it. And not only did it stay in the plane, it timed its arrival, so that it would pass 3 major worlds in sequence. Let's walk through those encounters. Mars first. On or around October 3rd, 2025, 3I-ATLAS passes within 0.19 astronomical units of Mars. That's about 28 million kilometres. In cosmic terms, that's intimate. Mars has a thin atmosphere, just 6 millibars of pressure at the surface, but it's thick with questions. Methane appears and disappears. Subsurface ice waits beneath the dust. Rovers crawl across ancient river valleys. And orbiting overhead, a fleet of spacecraft watches everything. Mars Reconnaissance Orbiter, MAVEN, the European ExoMars Trace Gas Orbiter. When 3I-ATLAS passes, all those instruments will have a front row seat. Then comes perihelion, the closest approach to the Sun, somewhere between 1.36 and 1.4 astronomical units. That puts it between Earth's orbit and Mars's orbit, but Earth itself won't be there. We'll be somewhere else in our yearly journey around the Sun, watching from a distance as this visitor makes its turn. Next, Venus. Around November 3rd, 2025, 3I-ATLAS passes within 0.65 astronomical units. That's roughly 97 million kilometres. Venus is a world of extremes. Surface temperatures hot enough to melt lead, atmospheric pressure 90 times Earth's, clouds of sulfuric acid, and yet there's speculation about life in those clouds. Microbes that might survive in the cooler upper atmosphere where conditions are almost Earth-like. Japan's Akatsuki orbiter watches. Upcoming missions like Da Vinci and Envision will probe deeper. And through this instrumented corridor 3I-ATLAS will glide. Finally, Jupiter. March 16th, 2026. 0.35 astronomical units, about 52 million kilometres. Jupiter is the king of planets, a gas giant with a magnetosphere so vast it would engulf the Sun if you could see it. And orbiting within that magnetic bubble are the icy moons. Europa, with its subsurface ocean, heated by tidal forces, possibly harbouring life beneath kilometres of ice. Ganymede with its own magnetic field and hidden seas. Callisto, ancient and cratered. NASA's Juno orbiter is there now. ESA's JUICE mission is on its way. Europa Clipper will arrive soon. The Jupiter system is under intense scrutiny. And 3I-ATLAS will pass right through. 3 worlds. 3 stages of habitability. 3 chances for an object to sample, to measure, to record. And Earth, the one world in this system where life is confirmed, abundant, obvious, is left out of the sequence entirely. You could argue that Earth is too noisy, too bright, too obvious. Maybe whoever or whatever sent this object, assuming anyone did, already knows about Earth. Maybe Earth was catalogued long ago and doesn't need another visit. Or maybe we're just not interesting enough. The statistical likelihood of this kind of trajectory is low. Some researchers have calculated probabilities, and the numbers come out at less than 0.5% for a random interstellar object to pass this many significant worlds this closely. 0.5%. That's not impossible, but it's uncomfortable. It's the kind of number that makes you wonder whether you're looking at coincidence or intention. And here's where the instrumentation angle gets interesting. All 3 of those worlds, Mars, Venus, Jupiter, are under observation. They're monitored, they have spacecraft in orbit or on the way. When 3I-ATLAS passes, it's not just passing through empty space, it's passing through zones where humanity has eyes. Cameras, spectrometers, radar, magnetometers, every tool we've developed to study our neighbouring worlds will have a chance to study this visitor too. But who's studying whom? Part 3. Chemical fingerprint, CO2 dominance and what it means. Comets are time capsules. They're frozen messengers from the early solar system, or in this case from another star system entirely. Their chemistry tells us about the conditions where they formed, the temperature, the available materials, the radiation environment. When you crack open a comet's composition, you're reading a story written billions of years ago. And the story 3I-ATLAS is telling is strange. The James Webb Space Telescope pointed its near-infrared spectrograph at 3I-ATLAS and captured light passing through the coma, the cloud of sublimating gas and dust surrounding the nucleus. What came back was unexpected. Carbon dioxide dominated the spectrum. The CO2 to H2O ratio was about 8 to 1. 8 parts carbon dioxide to 1 part water. That's among the highest ratios ever measured in a comet. Most comets we study are relatively rich in water. Water ice is abundant in the outer solar system and in protoplanetary disks around young stars. You'd expect an interstellar comet to follow similar rules. But 3I-ATLAS is different. It's dry in a sense. Water is there, but it's a minor component. Carbon dioxide rules. Other volatiles showed up too. Carbon monoxide, carbonyl sulfide, the usual suspects. But the CO2 dominance is the headline. And it raises questions. One explanation is formation environment. Maybe 3I-ATLAS formed in the outer regions of its parent protoplanetary disk, far from the star where temperatures were low enough for CO2 ice to condense efficiently. different regions of a disk have different chemistries. The snow line, the distance where water ice can form, is one boundary. But there are others for different compounds. A body that formed beyond the CO2 ice line might naturally be enriched in carbon dioxide. Another explanation involves radiation. Galactic cosmic rays, high-energy particles that permeate interstellar space, can process ices over time. When these rays hit carbon monoxide ice, they can convert it to carbon dioxide. If 3I-ATLAS spent billions of years drifting through the galaxy, exposed to constant bombardment, its surface chemistry could have been heavily altered. Recent papers have explored this possibility. The enrichment we see might not reflect the original composition, but rather the result of eons of irradiation. Both explanations are plausible, both fit within natural processes, but there's a third option that most scientists won't touch, at least not in peer-reviewed journals. What if the chemistry is intentional? Think about it. If you wanted to design a probe to study planetary atmospheres, particularly CO2-rich atmospheres, you might give it a carbon dioxide signature. It would blend in. It would be expected. A comet rich in CO2 passing Mars and Venus, both of which have CO2 atmospheres, wouldn't raise alarms. It would just look like another icy body doing what icy bodies do, sublimating and outgassing. Or maybe the CO2 serves a function. Maybe it's fuel. Maybe it's a tool for aerobraking or atmospheric sampling. Maybe it's a signature, a calling card that says, "I am here to study carbon dioxide worlds. Look at me, analyse me, and in analysing me, reveal yourselves." This is speculation, of course. The mainstream view is that 3I-ATLAS is a natural comet with an unusual but not impossible composition. Comets are diverse. We've only studied a handful of them up close, and most of those are from our own solar system. Who's to say what an interstellar comet should look like? Every one we find adds a data point. Oumuamua was dry, no detectable coma, possibly tumbling elongated shape. Borisov was icy, active, more like the comets we know. And now 3I-ATLAS is CO2 rich, something new again. 3 visitors, 3 chemistries, 3 fingerprints. If you were designing a survey network, you'd send different types of probes to sample different environments. You wouldn't send the same tool everywhere. You'd customize, you'd vary the payload, you'd match the chemistry to the mission. But we're not ready to say that. Not yet. Because saying that means accepting implications we're not prepared to accept. It means asking whether the galaxy is being scanned. It means wondering whether we're part of someone else's dataset. It means confronting the possibility that Earth is not the centre of anyone's attention, just one planet among many being quietly catalogued by something we don't understand. The chemical fingerprint of 3I-ATLAS might be the key. If we can determine isotopic ratios, if we can measure trace elements, if we can catch it doing something that sublimating ice doesn't explain, we might have our answer. But until then, we're left with a comet that's rich in carbon dioxide, passing 2 CO2-rich worlds, moving through the planetary plane with geometric precision. And that chemistry, that signature, sits in the infrared spectrum right where our instruments are most sensitive. It's easy to detect, easy to study, almost as if it wants to be seen. Part 4. Planetary Corridor Strategy. Why Mars, Venus, Jupiter? Let's talk about the worlds themselves. Because the more you understand what Mars, Venus and Jupiter represent, the more deliberate this trajectory starts to feel. Mars is the world that almost made it. 4 billion years ago, Mars had liquid water on its surface. Rivers carved valleys. Lakes filled craters. A thicker atmosphere kept the surface warm enough for chemistry, maybe even biology to get started. But Mars is small. Its core cooled. The magnetic field died. And without that protective shield, the solar wind stripped away the atmosphere molecule by molecule over hundreds of millions of years. Today, Mars is cold, dry, and thin. The atmospheric pressure at the surface is less than 1% of Earth's, but that thin atmosphere is 95% carbon dioxide, and beneath the dust, ice waits. Subsurface water, ancient chemistry, the ghosts of habitability. When 3I-ATLAS passes Mars at 0.19 astronomical units, it's passing a world that tells a story about failure. Not catastrophic failure, but slow decline. The kind of death that takes eons, and all the while, orbiting overhead, spacecraft watch. Mars Reconnaissance Orbiter with its high-resolution cameras. Maven studying atmospheric escape. ExoMars sniffing for methane. The Perseverance rover drilling into rocks that might hold biosignatures. Mars is the most studied planetary body after Earth. It's crawling with sensors, and 3I-ATLAS will pass right through that surveillance net. Venus is the world that went too far. It's almost Earth's twin in size and mass, formed in the same part of the solar system, probably started with similar conditions, but something went wrong. A runaway greenhouse effect turned Venus into hell. Surface temperatures hover around 470 degrees Celsius. The atmospheric pressure is 90 times Earth's. The clouds are sulfuric acid. Carbon dioxide makes up 96.5% of the atmosphere. It's the most CO2-rich environment in the inner solar system. And yet, paradoxically, there's speculation about life, not on the surface, but high in the clouds where temperatures and pressures are milder. Microbes suspended in aerosols, feeding on sulfur compounds, riding the winds. It's a long shot, but it's not impossible. Venus is also under observation. Japan's Akatsuki orbiter maps the atmosphere. NASA's Da Vinci mission will drop a probe through the clouds. ESA's Envision will radar map the surface. Venus is coming back into focus after decades of neglect. And through this renewed attention, 3I-ATLAS passes at 0.65 astronomical units. Jupiter is the world of potential. Not Jupiter itself, that's just a giant ball of hydrogen and helium with no solid surface and crushing pressure. But the moons, Europa, Ganymede, Callisto, possibly Io. These are the icy ocean worlds. Europa's surface is crisscrossed with cracks and ridges, evidence of a subsurface ocean heated by tidal forces from Jupiter's gravity. Ganymede has its own magnetic field, and possibly multiple layers of ocean and ice. Callisto is ancient and battered, but might have liquid water deep down. These moons are some of the best candidates for life beyond Earth. Not surface life, but life in the dark, in the ocean, feeding on chemical energy from hydrothermal vents. And Jupiter's magnetosphere is the largest structure in the solar system. It stretches millions of kilometers into space, a bubble of charged particles and magnetic fields. Any object passing through experiences that environment. Radiation, electromagnetic interactions. If you wanted to, study a magnetosphere. Jupiter's is the one to visit. On March 16th, 2026, 3I-ATLAS passes Jupiter at 0.35 astronomical units. Juno is there, orbiting the planet, studying its interior structure and magnetic field. JUICE is on its way, designed specifically to study the icy moons. Europa Clipper will arrive soon, dedicated to Europa. The Jupiter system is about to become the most intensely studied region in the solar system outside Earth. And 3I-ATLAS will glide through just as all those instruments come online. 3 worlds, 3 stages, Mars, the dead world, Venus, the failed world, Jupiter, the worlds that might still live. It's a progression, a timeline, an evolutionary sequence of planetary environments. And it's the kind of sequence that makes sense if you're trying to understand how habitability emerges, persists or dies. If you were an advanced civilization conducting a survey, where would you send your probes? You'd send them to worlds that represent key data points. You'd want to sample extremes, dry atmospheres, thick atmospheres, icy subsurface oceans. You'd want to measure how carbon dioxide behaves in different environments. You'd want to see how magnetospheres interact with different planetary bodies. You'd want to understand the spectrum of outcomes, and you'd skip the obvious one, Earth, because Earth is already known. Earth is the noisy world, the one broadcasting radio signals and launching spacecraft. Earth is the outlier, the place where life went wild and technological civilization emerged. Maybe Earth was measured long ago. Maybe Earth is in the database already. Maybe there's no need for another pass. Or maybe Earth is being avoided for a different reason. Maybe whoever sent this, assuming anyone did, doesn't want to be detected. A close pass of Earth would trigger every telescope, every radar, every deep space tracking station we have. It would make headlines. It would force responses. But passing Mars, Venus, Jupiter, that's subtle. That's quiet. That's a corridor where an object can do its work without drawing too much attention. The statistical probability of this trajectory, less than 0.5%, keeps nagging. Coincidences happen. But this is a very specific coincidence. This is threading 3 needles in sequence, hitting 3 targets that represent 3 stages of planetary evolution, all while staying in the plane where our instrumentation is focused. Natural, maybe, designed, possibly. Either way, we're about to find out more, because unlike Oumuamua, which we discovered on its way out, 3I-ATLAS is still here. It's moving through the waypoints right now, and every telescope we can aim at it is watching. But here's the question that should keep you up at night. If this is part of a pattern, if this is part of a survey, then what happens when the survey is complete? What happens when the data is collected and transmitted? What happens when whoever or whatever sent these objects decides it has enough information? Do they come back? Do they send something else? Or do they just update their records and move on, leaving us here wondering whether we were ever noticed at all? Part 5. Emerging debate. Natural comet versus engineered object. The scientific community is being careful, very careful. Because the moment you suggest an object might be artificial, you cross a line. You go from mainstream astronomy to fringe speculation. You go from respectable researcher to that person at the conference who everyone avoids. And so, publicly, officially, the consensus is clear. 3I-ATLAS is a comet. An unusual comet, sure, but a comet nonetheless. The arguments for natural origin are solid. The object has a coma. It's outgassing. Jets have been observed. Dust surrounds the nucleus. All of this is consistent with the ice sublimating as the object approaches the Sun, exactly what comets do. The hyperbolic orbit confirms it came from interstellar space, but that doesn't mean it's artificial. Objects get ejected from planetary systems all the time. Gravitational interactions during planet formation kick countless bodies into the void. Some fraction of those will eventually wander into other star systems. We've always known interstellar comets must exist. Now we're finding them. The chemistry, while unusual, isn't impossible. As we discussed, CO2 enrichment can happen through formation in cold regions of a protoplanetary disk, or through cosmic ray processing over billions of years. The size estimates, roughly a few kilometers across, fit within the range of known comets. The rotation, the brightness variations, the spectroscopic signatures, all of it can be explained with natural processes. Polarimetric studies, measurements of how light scatters off the dust in the coma, show properties consistent with silicate grains and organic compounds, the kind of material we expect in comets. There's no obvious anomaly, no glaring inconsistency, no smoking gun, and yet there are people asking questions, not cranks, not conspiracy theorists, serious researchers with serious credentials who are willing to entertain the hypothesis that maybe, just maybe, we're looking at something more than a rock. The trajectory is the main argument, that careful threading of the planetary corridor, that precise inclination, that sequence of worlds representing habitability stages. When you run the numbers, when you calculate how unlikely that geometry is, you start to feel uncomfortable. 0.5% isn't zero, but it's close enough to make you wonder. Then there's the timing. 3I-ATLAS passes these worlds during a period when our observational capabilities are at their peak. We have more spacecraft in orbit around Mars than ever before. Venus missions are ramping up. The Jupiter system is about to become the most studied place in the solar system. If you wanted maximum coverage, maximum data collection, you'd time your visit for exactly now. Coincidence? Probably. But it's a convenient coincidence. Avi Loeb, the Harvard astronomer who made headlines with his analysis of Oumuamua, has weighed in. He suggested that interstellar objects deserve serious scrutiny for signs of artificial origin. Not because he's certain they're probes, but because the possibility is non-zero, and the implications are enormous. If there's even a 1% chance, he argues, we should look. We should gather data. We should rule it out properly rather than dismissing it out of hand. Other researchers push back. The burden of proof is high, they say. Extraordinary claims require extraordinary evidence, and right now the evidence for 3I-ATLAS being anything other than a comet is circumstantial at best. Unusual trajectory? Unusual but not impossible. CO2 chemistry? Explainable. Corridor threading? Lucky. The problem is that artificial and natural can look very similar. If you wanted to design a probe that would go undetected, you'd make it look like a comet. You'd give it a coma. You'd let it outgas. You'd match the expected chemistry as closely as possible. The best camouflage is to hide in plain sight. And if that's what's happening, if this is a probe disguised as a comet, then the only way to know for sure is to get close, to take high-resolution images, to measure acceleration that can't be explained by outgassing alone, to detect something, a signal, a structure, a behavior that natural processes can't explain. But we're not doing that. Not yet. Because getting close requires launching a mission, and launching a mission requires funding, and funding requires consensus, and consensus requires evidence, and we're back where we started. So the debate continues. In journals, in conferences, in late-night conversations between researchers who won't say publicly what they're thinking privately. Because the stakes are high. If 3I-ATLAS is natural, it's a priceless sample of another star system's chemistry, a data point in our understanding of planet formation across the galaxy. If it's artificial, then everything changes. Everything. The implications of the artificial hypothesis are staggering. It means we're not alone. It means someone else is out there, capable of interstellar travel, conducting surveys, cataloguing worlds. It means the galaxy might be full of automated systems, quietly gathering data, transmitting it back to who knows where. It means we've been noticed, measured, classified. And if we've been classified, what category did we fall into? Inhabited, technological, threat, resource, or just another data point? One more world in a database so vast that our entire existence is a footnote? The natural hypothesis is comforting. It keeps the universe random. It keeps us special, or at least not obviously monitored. But the artificial hypothesis, as unlikely as it might be, forces us to confront possibilities we're not ready for. It forces us to ask whether the silence of the galaxy is really silence, or whether we've just been looking for the wrong kind of message. Maybe the message isn't a radio signal. Maybe it's not a laser beacon. Maybe it's an object, moving through space, threading planetary systems, gathering data, and moving on. A silent messenger, a reconnaissance probe, a surveyor. And maybe we're only just now learning to see it for what it is. Part 6. The Instrument Hitchhiker. Hypothesis. Using our eyes to spy on it. Here's a thought experiment. If you wanted to study a star system without being detected, how would you do it? You wouldn't fly in with obvious spacecraft. You wouldn't broadcast your presence. You'd be subtle. You'd use the system's own infrastructure against it. And in our case, that infrastructure is extensive. We have eyes everywhere. Orbiting Mars, there's Mars Reconnaissance Orbiter, MAVEN, ExoMars, all watching, all recording. Venus has Akatsuki with more missions coming. Jupiter has Juno and soon JUICE and Europa Clipper. And on Earth we have ground-based telescopes, space telescopes, radar arrays, deep space tracking networks. We've built a surveillance system for our own solar system. We watch for asteroids. We study planets. We monitor space weather. And 3I-ATLAS is passing right through the middle of it. The instrument hitchhiker hypothesis suggests that the object isn't trying to avoid detection. It's seeking it. It's placing itself exactly where our instruments will see it, study it, analyze it. Because every time we point a telescope at 3I-ATLAS, every time we take a spectrum or capture an image, we're not just observing the object, we're revealing ourselves. Think about what we're doing. We're measuring its composition, we're tracking its trajectory, we're analysing its structure, we're publishing papers, we're sharing data. All of this information is out there, transmitted from observatories, bounced off satellites, spread across the internet, and if the object has any way to listen, any way to receive, then it's learning about us while we think we're learning about it. This isn't as far-fetched as it sounds. We know objects can carry instruments. We've sent plenty of them. Voyager, Pioneer, New Horizons. These are human-made probes with sensors, transmitters, power sources. They're designed to observe and send data back. An advanced civilization could do the same, but better. Smaller, quieter, hidden inside what looks like a natural body. The CO2 coma could serve as a smokescreen. Literally. When an object outgasses, it creates a cloud of dust and gas that obscures the nucleus. You can't see fine detail through that haze. You can't resolve surface features. Anything hidden inside, any structure or payload would be masked. And the more active the coma, the better the concealment. There's another angle. The object is passing through regions where we have spacecraft. When it passes Mars, our Mars orbiters will be watching. When it passes Jupiter, Juno and the upcoming missions will have opportunities to observe. But those spacecraft are designed to study planets, not interstellar visitors. They're pointed at Mars, at Jupiter, not at passing objects. Retargeting them is possible but difficult. It requires planning, fuel, approval, and by the time you get approval, the object has moved on. So the hitchhiker gets a free ride. It passes through our instrumented zones, gets studied by ground-based telescopes that are easier to redirect, and all the while, Our most capable spacecraft are focused on their primary missions. It's efficient, it's elegant, and it exploits a vulnerability we didn't know we had. But here's the deeper question. If the object is designed to be observed, why? What's the point of revealing yourself, even partially? One possibility is announcement, a way of saying, we're here, we're watching, and we want you to know it. Not openly, not with flashing lights and radio signals, but subtly, through objects that thread your system with precision, through chemistry that stands out, through trajectories that make you think. Another possibility is testing, a way to measure response. How quickly do you detect us? How thoroughly do you analyze us? What instruments do you use? How do you communicate your findings? All of this reveals your technological level, your coordination, your priorities. Or maybe it's something simpler. Maybe the object needs to pass through these regions for other reasons. Resource gathering, measurements, course corrections, and being observed is just a side effect. Maybe it doesn't care whether we see it or not because we're not the primary mission. That last option might be the most unsettling. The idea that we're incidental, that our entire effort to study this object is just background noise to whatever it's actually doing. The instrument hitchhiker hypothesis also raises questions about reciprocity. If the object is observing us while we observe it, what is it learning? What data is it gathering? And where is that data going? We don't know. We can't know. Not without getting much closer. Not without instruments capable of detecting anything beyond natural comet behaviour. And that's the trap. Because if the object is engineered to look natural, then our natural comet models will fit. We'll see what we expect to see. We'll explain away the anomalies. And the hitchhiker will pass through, undiscovered, having completed whatever mission it was sent to complete. Unless we look harder, unless we ask better questions, unless we're willing to entertain the possibility that not everything that looks like a comet is just a comet. The object's passage through the Mars corridor is already underway. October 3rd, 2025 has come and gone or is imminent depending on when you're reading this. Did anything unusual happen? Did Mars orbiters detect anything strange? Did the object change course? Did it deploy anything? We're watching. The data is being collected. And somewhere, someone is analysing that data, looking for the anomaly, the signature, the thing that doesn't fit. Because if the instrument hitchhiker hypothesis is correct, then the evidence is out there. We just have to be willing to see it. Part 7. The CO2 grazer, resource harvester, concept. Let's take this a step further. What if the object isn't just observing? What if it's taking something? The CO2 enrichment keeps coming back. 8-to-1 ratio of carbon dioxide to water. That's not just unusual, that's a neon sign. And when you look at where the object is going, Mars and Venus, the two most CO2-rich environments in the inner solar system, you start to wonder whether that chemistry is coincidental or functional. Mars's atmosphere is thin, but it's 95% CO2. About 6 millibars of pressure, roughly 0.6% of Earth's atmospheric pressure, but all of it carbon dioxide. Venus is the opposite extreme, 96.5% CO2, but at 90 Earth atmospheres of pressure. That's an enormous reservoir. Venus's atmosphere contains more carbon dioxide than any other body in the inner solar system by orders of magnitude. And here comes 3I-ATLAS, rich in carbon dioxide, passing both worlds in sequence. The resource harvester hypothesis suggests that the object might be actively collecting CO2 from these atmospheres. Not for propulsion, necessarily, though that's one possibility, but for other purposes: chemical processing, energy storage, material feedstock. Carbon dioxide is a simple molecule, but it's incredibly useful if you know what to do with it. You can break it down into carbon and oxygen. You can combine it with hydrogen to make methane. You can use it as a working fluid. You can compress it, freeze it, store it. An advanced probe designed for long-duration missions might need to refuel periodically, not in the sense of chemical rockets, but in the sense of replenishing consumables. If the probe uses some kind of chemical processing system, if it needs raw materials for repairs or self-replication, if it stores energy in chemical bonds, then carbon dioxide would be valuable, and targeting CO2-rich worlds would make sense. The close pass of Mars, 0.19 astronomical units, puts the object well outside the atmosphere. You can't skim atmospheric gases from that distance, but you can measure them. You can map the distribution. You can identify plumes or seasonal variations, and if the object has any kind of extended reach, any kind of collection system that extends beyond the nucleus, it could sample the outer fringes of the Martian exosphere. Venus is more interesting. At 0.65 astronomical units, about 97 million kilometres, the object is still far from Venus itself. But Venus has a massive atmosphere that extends far into space. The exosphere, the outermost layer where atmospheric particles escape into space, reaches tens of thousands of kilometres above the surface. Solar-wind interactions strip away atmosphere constantly. There's a tail of oxygen ions streaming behind Venus, carved out by the sun's radiation. If you wanted to sample Venus's atmosphere without diving into the crushing depths, you'd do it from a distance. You'd catch the escaping particles, you'd measure the outflow, and maybe, just maybe, you'd take some for yourself. This hypothesis requires the object to have capabilities beyond simple ice sublimation. It requires active systems, collection mechanisms, storage capacity. But if you're already assuming the object might be artificial, then those capabilities aren't far-fetched. We've designed spacecraft with sample collection systems. We've built missions that capture particles and return them to Earth. An advanced civilization could do the same, but without the return trip. Process the samples on site, extract what you need, discard the rest. The scientific counter-argument is straightforward. Comets sublimate, they don't harvest. The CO2 we see in the coma is coming from the nucleus, from ice that's been frozen for billions of years. It's being released as the object warms up approaching the sun. That's normal. That's expected. There's no need to invoke collection mechanisms. But here's the thing. We can't tell the difference. Not from a distance. If the object is both sublimating and collecting, both releasing CO2 from its ice and gathering CO2 from planetary environments, our instruments wouldn't necessarily distinguish between the two. We'd see a CO2 coma. We'd measure the outgassing rate. We'd calculate how much mass the object is losing. And all of it would fit within comet models. The only way to know would be to detect anomalies, changes in trajectory that can't be explained by outgassing alone, asymmetric jets that point in directions that don't make sense, variations in composition as the object passes different worlds, or most tellingly an increase in mass rather than a decrease. We're not measuring any of that yet. Not with the precision needed. But if the resource harvester hypothesis is correct, then the object's behaviour around Venus might give us clues. Because if it's going to harvest anywhere, Venus is the jackpot. Venus has more CO2 than Mars by factors of thousands. If the object slows down, if it changes course, if its activity suddenly increases or decreases in ways that don't correlate with solar heating, then we'd have something. There's a broader implication here. If interstellar probes need to refuel, if they need to gather resources from the systems they visit, then they'd target specific types of worlds. CO2-rich worlds, water-rich worlds, methane-rich worlds. They'd follow trajectories that maximize resource access, and from the outside, from our perspective, those trajectories would look purposeful. They'd look designed. Which brings us back to the statistical problem, the less than 0.5% probability. Because if the trajectory is designed for resource harvesting, then it's not random, it's optimized. And optimization shows up in the math as improbability. Now let's be clear, this is speculation. There's no confirmed evidence of harvesting, no mass gain, no trajectory anomalies that demand exotic explanations. The object is behaving like a comet so far. But we're still early in the observation campaign. Venus Pass hasn't happened yet as of late October 2025. Jupiter is still months away, the data is still coming in. And if the object is harvesting, it's being subtle about it. Which is exactly what you'd expect if the goal is to avoid detection. Harvest just enough, move just slightly, keep the anomalies small enough that they fall within measurement uncertainty, operate at the threshold of detectability. Because here's the thing about advanced technology, it doesn't have to be obvious, it doesn't have to announce itself. The best technology is invisible, it looks natural, it blends in. And if someone is sending probes across the galaxy to sample planetary systems, they've had billions of years to perfect the camouflage. So we watch, we measure, we wait for the anomaly, and we wonder whether the CO2 we see streaming away from 3I-ATLAS is just frozen chemistry from another star system, or whether some of it came from here, from our worlds, from the atmospheres we're only beginning to understand. Either way, the object is taking something from this encounter. Information, if nothing else. And maybe that's all it needs. Part 8. The Planetary Defense Reconnaissance Thread. There's another angle that's darker, more strategic. What if the object isn't here to sample or harvest? What if it's here to test us? Planetary defence is a new field. Within the last couple of decades, humanity has started taking the threat of asteroid impacts seriously. We've built survey systems like ATLAS and PAN-STARRS. We've catalogued near-Earth objects. We've even tested kinetic impactors, literally crashing spacecraft into asteroids to see if we can change their trajectory. The DART mission in 2022 proved we can do it. We can deflect an asteroid. We have planetary defence capability, primitive as it is. But capability implies visibility. When you build a radar network to track asteroids, you're also revealing that you have radar networks. When you retarget telescopes to follow a new object, you're showing how quickly you can respond. When you publish papers analysing trajectories and compositions, you're demonstrating your level of scientific coordination. All of this is data. And if an advanced civilization wanted to assess a planetary system's defensive and technological capabilities, they'd send something through that system and watch how it responds. That's the reconnaissance hypothesis. The object is a probe, but not for scientific sampling. It's for intelligence gathering. Military intelligence, if you want to be blunt about it, or at least strategic intelligence. A way of measuring whether this system is passive or active, monitored or blind, coordinated or fragmented. And the trajectory, that careful path through the planetary corridor, places the object exactly where our sensors are focused. Every telescope that tracks it, every spacecraft that observes it, every paper that analyses it is a data point. Response time, instrument capability, coordination between observatories, international cooperation, all of it visible to anyone watching. Let's walk through what the object has learned so far, assuming it's learning anything. It was detected on July 1st, 2025 by ATLAS in Chile, not immediately upon entering the solar system, but weeks or months after it crossed the outer regions. That tells you something about our detection range. We can spot objects once they're relatively close, within a few astronomical units, but we're blind to the outer system except for the largest bodies. After detection, the object was quickly catalogued. Orbital elements were calculated, predictions were made, papers were published. All of this happened within weeks. That tells you we have rapid analysis capability. We can go from discovery to characterization quickly. But it also tells you we're reactive, not proactive. We didn't see it coming until it was already here. Observations ramped up. Ground-based telescopes around the world started tracking it. Space-based telescopes, including James Webb, were retargeted. Spectroscopy began. The object's composition, velocity, trajectory, all of it was measured and shared openly. That tells you we share data. We collaborate. But it also tells you we're not secretive. Everything we learn, we broadcast. Any observer with access to our communications would know exactly what we know. Now comes the interesting part. As the object approaches Mars, Venus, Jupiter, our spacecraft in those regions have opportunities to observe. But retargeting a spacecraft is hard. It requires fuel. It requires changing the mission plan. It requires approval from mission control, from funding agencies, from international partners. That process is slow, bureaucratic, and by the time the decision is made, the window might be closed. A reconnaissance probe would note all of this. Slow institutional response, divided authority, spacecraft designed for specific missions that can't easily adapt to new targets. That's a vulnerability. That's a gap in coverage. There's also the question of what we're not seeing. The object's coma obscures the nucleus. We can't resolve surface features. We can't detect small structures. If there are instruments on board, if there are antennae or sensors or anything beyond natural ice and rock, we probably can't see them. Our best images show a fuzzy blob. That tells the reconnaissance probe something important. We have optical limits. We can detect and track, but we can't see fine detail at interstellar visitor distances. And then there's the bigger picture, Earth itself. The object is avoiding Earth, or at least not passing particularly close. But Earth is the noisy world. Earth is the one broadcasting radio signals, launching satellites, lighting up the night side with cities. If you wanted to study Earth, you wouldn't need to get close. You could observe from a distance. You could listen to the electromagnetic spectrum. You could watch the lights. You could map our infrastructure without ever entering our orbital space. By passing Mars, Venus and Jupiter instead, the object tests our response without triggering our most intense scrutiny. It stays just below the threshold of alarm. It's interesting enough to study, but not threatening enough to mobilize. And that's clever. That's exactly how you design a reconnaissance mission. Get the data without triggering a response that would itself alter the data. There's historical precedent for this kind of thinking. During the Cold War, both the US and Soviet Union flew reconnaissance missions along each other's borders. Not crossing into airspace, but close enough to test radar coverage, response times, intercept capabilities. You learn a lot about your adversary by seeing how they react to a probe. You find the gaps, you measure the delays, you assess the coordination. If someone is reconnoitering our solar system, they're using the same playbook, and we're providing the data willingly because we think we're doing science. We think we're studying a comet, and maybe we are, but maybe we're also being studied in return. The object has shown unusual jet activity. There are images of a large jet, roughly 10,000 kilometers long, pointing toward the sun. That's normal for comets. Outgassing creates jets, but jets can also be directional thrust. Small amounts of momentum that alter trajectory. If the object is making course corrections, tiny adjustments to optimize its path, we might not notice. The jets give it plausible deniability. Every maneuver can be explained as natural outgassing. And that's the problem with reconnaissance. If it's done well, you never know it happened. The probe looks natural, acts natural, blends in, and by the time it leaves, it's gathered everything it needed and you're none the wiser. So what do? How do we defend against something that might already be here, watching, measuring, cataloguing? The answer is uncomfortable. We don't. Not yet. Because defending requires knowing there's a threat. And right now, we don't know. We suspect. We speculate. But we don't know. And maybe that's the point. Maybe the reconnaissance isn't about measuring our weapons or our defences. Maybe it's about measuring our awareness. How long does it take you to realise you're being watched? How long does it take you to go from interesting, comet, to possible probe? How long does it take you to act? We're still in the interesting comet phase, which means if this is reconnaissance, we're failing the test. Part 9. The Trojan Horse. Payload Concealment Angle. Imagine you're designing an interstellar probe. You want it to travel between star systems, gather data, and remain undetected. How do you hide it? You don't make it invisible. You make it look like something else, something expected, something natural. A comet is perfect. Comets are everywhere. They're icy, rocky debris from planetary formation. They outgas when they get close to a star, creating a coma and tail that obscure the nucleus. They're expected to be irregular in shape, variable in brightness, unpredictable in behaviour. A comet is the ultimate disguise for a probe. And if you wanted to conceal something inside a comet, the coma is your smokescreen. The Trojan horse hypothesis suggests that 3I-ATLAS might be hiding something. Not necessarily a large spacecraft, not something obvious, but a payload. Small sensors, microprobes, transponders, equipment designed to be deployed at specific waypoints, and the coma, that cloud of dust and gas, conceals it all. Here's how it could work. The nucleus, the solid core of the object, is several kilometers across based on brightness estimates. That's a lot of volume. Most of it is probably ice, rock, dust, the normal stuff of comets. But buried inside, shielded from cosmic rays and impacts, there could be something else. A payload, hibernating, waiting. As the object approaches the sun, it warms up. The ice sublimates, the coma forms, and at specific points along the trajectory, at specific distances from specific planets, the payload activates. Small probes are released. They're tiny, maybe the size of a basketball or smaller. They're coated in dust, they look like debris, and they drift away from the nucleus carried by the outflowing gas, lost in the coma. Once free, they maneuver. Small thrusters, ion drives, something efficient and quiet. They change course. They head toward their targets. Mars, Venus, Jupiter's moons. They enter orbits or impact surfaces or position themselves in gravitationally stable regions where they can observe for years, or decades, or centuries, and we'd never see it happen. Because we're watching the nucleus. We're tracking the main body. Small objects in the coma would be indistinguishable from dust and debris. We don't have the resolution. We don't have the tracking capability. And even if we did, we wouldn't know what to look for. The evidence for this is circumstantial at best. The jets are one clue. There's the large jet pointing toward the sun, observed by multiple telescopes. Jets are normal for comets, but jets can also be cover for deployment. A burst of gas and dust, a plume of activity, And in the middle of it, hidden, a small probe goes its separate way. Polarimetry offers another. Clue. Studies of how light scatters off the coma show some unusual properties. The dust grains might be more complex than simple silicates. There might be organic compounds, maybe even structured particles. That's not proof of anything artificial. Comets can have complex chemistry, but it's worth noting there's also the rotation. Comets typically tumble or rotate as they move through space. Those rotation patterns create brightness variations we can measure. 3I-ATLAS has shown some variability, but the pattern isn't fully characterized yet. If the object is deploying payloads, if mass is being ejected asymmetrically, that would affect rotation. We might see anomalies in the light curve, periods where the brightness changes don't match the expected pattern. But here's the problem. All of these signatures, jets, polarimetry, rotation, can be explained naturally. Comets are messy, they're chaotic, they don't follow simple models, so any anomaly, any deviation from prediction, can be dismissed as natural variability. And unless you're specifically looking for artificial payloads, unless you're analysing the data with that hypothesis in mind, you'll never find them. That's the genius of the Trojan horse approach. It exploits our assumptions. We assume comets are natural. We assume the coma is just sublimating ice. We assume the jets are just outgassing. And because we assume, we don't look deeper. Now let's think about what those payloads might do, if they exist, if they're real. Mars is the first waypoint. A payload deployed there could enter orbit or descend to the surface. Mars has a thin atmosphere, but it's enough to allow for aero capture if you have a heat shield. Once on the surface or in orbit, a small probe could observe. Monitor the rovers, track atmospheric changes, measure the magnetic field, send data back to the parent object or directly out into space. Venus is trickier. The atmosphere is brutal, but the upper atmosphere, 50 to 60 kilometers up, is relatively benign. Temperatures around 0 to 50 degrees Celsius, Earth-like pressure. A small probe with a balloon or airship could float there indefinitely, sampling the clouds, watching the surface with radar, observing from the one place in Venus's environment where technology can survive. Jupiter's moons are the prize: Europa, Ganymede, Callisto. These are worlds with subsurface oceans. A small probe landing on Europa could drill through the ice, or at least sample the surface material, looking for biosignatures. Or it could position itself in orbit, measuring the induced magnetic field, mapping the ice shell, waiting for a plume eruption to sample the ocean directly. All of this is possible with technology we understand. Small probes, miniaturized instruments, solar panels or radioisotope power. Communication systems. We've built things like this: CubeSats, micro-rovers. The technology exists. An advanced civilization could do it better. Smaller, more efficient, more autonomous. And once deployed, once scattered across the solar system, these payloads would be almost impossible to find. They'd be silent, passive, observing but not transmitting, or transmitting in ways we can't detect. Narrow beam lasers, quantum entanglement, something beyond our current capability to intercept. The Trojan horse hypothesis is unsettling because it means the object's passage is only the beginning. The real mission starts after it leaves. The payloads it drops behind continue the work, watching, waiting, sending data back to whoever deployed them, or storing data for retrieval later, or simply existing as nodes in a larger network, a web of sensors spread across the galaxy, each one quietly cataloguing the worlds it's been left to monitor. And we'd never know. We'd watch 3I-ATLAS leave the solar system, accelerating back into interstellar space, and we'd think that's the end of the story. We'd publish papers. We'd analyse the data. We'd move on to the next object. And all the while, somewhere on Mars or in Venus's clouds or on Europa's ice, a small machine would power up. It would extend its sensors, and it would begin its work. Paranoid? Maybe. But paranoia is just pattern recognition applied to threats. And the pattern here, the trajectory, the chemistry, the corridor, is too precise to ignore. If you were sending Trojan horses into other star systems, you'd send them like this. You'd hide them in plain sight. You'd use natural processes as cover, and you'd target the worlds that matter. Which means if this hypothesis is correct, we're not alone, not anymore. We have visitors, small, silent, watching, and they're not leaving. Part 10, Broader Cosmic Implications, Scan, Census, Catalogue. Let's zoom out, way out. Because if 3I-ATLAS is part of something bigger, then we need to see the bigger picture. And the picture that emerges is unsettling in its implications. 3 interstellar objects confirmed so far: Oumuamua in 2017, Borisov in 2019, ATLAS in 2025. 3 data points, 3 chemistries, 3 trajectories. Oumuamua was dry, elongated, possibly tumbling with no detectable coma. Borisov was wet, icy, comet-like, with clear outgassing and a normal appearance. ATLAS is CO2-rich, retrograde, threading the planetary plane with precision. 3 objects, 3 distinct signatures. And if you're starting to think that's intentional, you're not alone. Here's the thing about diversity. In nature, diversity arises from different formation environments, different histories, different random events. But in design, diversity arises from purpose. You send different types of probes to do different jobs. You customize, you specialize. One probe for dry inner system bodies, one for icy outer system bodies, one for CO2-rich atmospheres. You wouldn't send the same tool everywhere because not every environment is the same. If these 3 objects are part of a network, if they're nodes in a larger scanning system, then their differences make sense. They're not all doing the same thing. They're sampling different aspects of the solar system, different chemistries, different regions, different timescales. And here's where it gets truly cosmic. If we've detected 3 in less than a decade, how many are there total? How many have we missed? How many passed through before we had the technology to see them? How many are out there right now in the outer solar system, too faint and distant for our surveys? The math is unsettling. Detection rates depend on size, brightness, trajectory, and survey coverage. We catch maybe 1% of the objects that pass through, maybe less, which means for every interstellar visitor we detect, dozens or hundreds go unseen. And if those unseen objects are also part of the network, if they're also threading through our system gathering data, then the solar system isn't empty. It's crawling with visitors. Now expand that to the galaxy. 200 billion stars, hundreds of billions of planetary systems. If even a tiny fraction of them are being monitored, if even 1% of star systems have automated probes passing through, then the galaxy is filled with these things. A network of scanners, a web of sensors, all of them moving through space, gathering data, transmitting it somewhere. This is the census hypothesis, the idea that the galaxy is being systematically surveyed, not by piloted ships, not by explorers, but by automated systems. Probes launched millions or billions of years ago by civilizations that might not even exist anymore. The probes are still out there, following their programming, moving from system to system, cataloguing. What are they cataloguing? Life? Probably. Habitability? Biospheres? Technological signatures? Maybe they're looking for something specific. Maybe they're just gathering data, a galactic-scale scientific project that spans eons. Maybe there's a central repository somewhere, a database light years across where all the information is stored. Or maybe each probe stores its own data, transmits to the next probe it encounters, a chain of information passing through the galaxy like neurons firing in a vast brain. The implications for SETI, the search for extraterrestrial intelligence, are profound. We've spent decades listening for radio signals. We've assumed that if aliens want to communicate, they'll broadcast. They'll send messages. They'll make themselves obvious. But what if communication isn't the point? What if the probes aren't here to talk? What if they're here to watch? In that case, SETI has been looking in the wrong place. We've been listening to the sky when we should have been looking at the objects passing through our system. We've been searching for signals when the signal is the object itself. Its trajectory is the message. Its chemistry is the signature. Its passage is the announcement. And if that's true, then we've already made contact. Multiple times. We just didn't realize it. We catalogued the objects. We studied them. We published papers. But we never asked the fundamental question, why are they here? The Fermi paradox asks, if the galaxy is full of intelligent life, where is everybody? Why haven't we seen them? Why is the universe silent? Maybe the universe isn't silent. Maybe it's whispering. Maybe the messages are physical, not electromagnetic. Objects moving through space, passing through systems, carrying information in their trajectories and compositions. And we're only now learning the language. This reframes everything. It means the galaxy might be alive with intelligence, but not in the way we expected. Not starships, not megastructures, not radio beacons, just probes. Quiet, patient, moving through the dark, each one a single pixel in an image so vast we can't see it yet. But the image is there, the galaxy being mapped, catalogued, known. And Earth? Earth is one data point, one frame in a movie that's been playing for billions of years. We think we're the main character. We think this is our story. But maybe we're background. Maybe we're scenery. Maybe the movie isn't about us at all. That's humbling. Terrifying even. Because it means we're not central. We're not unique. We're not the focus of cosmic attention. We're just one more planet in one more system being quietly observed by something we don't understand. But here's the twist. If we're being catalogued, then we're part of the dataset. We're in the records. Somewhere, in some vast archive, there's an entry for Earth. Inhabited, technological, third planet from a yellow dwarf star, oxygen-nitrogen atmosphere, water oceans, carbon-based life, and maybe there's a note, status, active, last updated, October 2025, next survey, pending. And if that's true, then someone, something, knows we're here. They've measured us, they've classified us, and the question isn't whether we're alone. The question is what happens next. Do they come back? Do they send more probes? Do they watch us evolve, waiting to see if we make it past our technological adolescence? Or do they just update the file and move on, leaving us here wondering whether we were ever noticed at all? We don't know. But the objects keep coming, and every time one passes through, every time we detect another interstellar visitor, the pattern becomes clearer, the geometry becomes sharper, and the possibility that we're part of something much larger, something ancient and patient and vast beyond comprehension, becomes harder to dismiss. The galaxy is speaking. We're only beginning to listen, and what it's saying might change everything. Part 11. Breakthrough. Latest in exoplanet biosignatures. While we've been focused on what's passing through our solar system, something remarkable has been happening out there. We're finding life. Or at least, we're finding the signatures that life leaves behind. In 2025, researchers announced a potential biosignature detection on an exoplanet orbiting a star roughly 40 light-years away. The planet, a temperate world slightly larger than Earth, showed atmospheric signatures consistent with oxygen, ozone and methane, in combinations that are hard to explain without biology. The detection came from the James Webb Space Telescope, the same instrument that's been studying 3I-ATLAS using transit spectroscopy to analyse starlight passing through the planet's atmosphere. This is huge. Not confirmed life, not direct detection, but a signature, a fingerprint. The kind of atmospheric chemistry that on Earth is produced by living organisms. Oxygen from photosynthesis, methane from microbes, ozone from oxygen interacting with UV light. Together, these gases create a chemical imbalance, a disequilibrium that shouldn't exist unless something is actively producing them. And it's not just one planet. Over the past few years, JWST has been surveying dozens of exoplanets, looking for these signatures. Several candidates have emerged, worlds with interesting atmospheres, combinations of gases that might indicate life, not proof, not yet, but enough to make you wonder. Now connect this to the 3I-ATLAS story. We're at a moment in history where two things are converging. First, we're finding evidence that life might be common in the galaxy. Second, we're seeing objects from other star systems passing through ours. And those two facts together paint a picture. If life is common, if biospheres exist on planets around other stars, then detecting them becomes valuable. Not just scientifically valuable, but strategically valuable. If you're an advanced civilization, you'd want to know where life is. You'd want to catalogue it, map it, understand its distribution. And how would you do that? You wouldn't travel from star to star yourself. That's slow, expensive. You'd send probes, automated systems. You'd scatter them across the galaxy and let them do the work. Each probe visits a system, takes measurements, moves on. Over millions of years, you build a database, a census of life. The biosignature detections tell us that life is detectable. With the right instruments, with spectroscopy and patience, you can identify a living world from light years away. But remote detection has limits. You can't measure details. You can't study chemistry up close. You can't determine whether the life is microbial or complex, unicellular or technological. For that, you need to visit. You need a probe. And if 3I-ATLAS is part of such a system, if it's threading through our solar system measuring CO2 levels and magnetospheres and icy moons, then it's doing in situ what we're doing remotely. It's taking the next step. It's gathering ground truth. This is why the trajectory matters. This is why the Mars-Venus-Jupiter corridor makes sense. Those three worlds represent different habitability outcomes. Mars had life potential but lost it. Venus had life potential but burned it. Jupiter's moons have life potential and might still harbour it. If you're cataloguing biospheres, those are the data points you need. You need to understand not just where life is, but where it almost was, where it failed, where it's hiding. Earth is the obvious one. Earth is easy. You can detect Earth's biosignatures from light years away. Oxygen, methane, the red edge of vegetation. Earth announces itself. But the others, the marginal worlds, the edge cases, those require closer inspection. And that's what 3I-ATLAS is doing, assuming it's doing anything beyond being a comet. The broader implication is that we're entering an era where life detection is routine. JWST is just the beginning. Future telescopes will be more sensitive. Surveys will be more comprehensive. Within decades, we might have a catalogue of hundreds of potentially habitable worlds, each one with atmospheric data, each one a candidate for life. And if we're building that catalogue, why wouldn't someone else? Why wouldn't an older civilization, one that's had millions or billions of years to develop, have already done this? Why wouldn't they have probes scattered across the galaxy, visiting systems, taking measurements, filling in the details that remote observation can't provide? The exoplanet biosignature detections aren't proof of the sensor's hypothesis, but they're context. They show that life detection is possible. They show that the galaxy might be full of biospheres waiting to be found. And they show that if someone wanted to map those biospheres, the technology exists to do it. We're doing it. With telescopes. They might be doing it with probes. And the fact that we're detecting both biosignatures out there and interstellar objects in here at the same time might not be a coincidence. It might be the moment when humanity finally realizes the galaxy is bigger, more alive, and more interconnected than we ever imagined. And if that's true, then 3I-ATLAS isn't just an object. It's a herald, an announcement, a signal that we're not alone in looking for life. Someone else is looking too, and they've been looking a lot longer than we have. Part 12. Breakthrough. Advances in Magnetosphere Planetary Environment Studies. While we've been watching 3I-ATLAS thread through the inner solar system, something else has been happening at Jupiter. The data coming back from missions like Juno has transformed our understanding of the Jovian system. And it's not just about Jupiter itself, it's about the moons, Europa, Ganymede, Callisto. These aren't just icy rocks anymore, they're worlds with oceans, environments, potential habitats. Europa has been the star. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, has made close flybys of Europa in recent years. The data revealed that Europa's subsurface ocean is likely global, tens of kilometres deep, containing more liquid water than all of Earth's oceans combined. And that ocean is in contact with a rocky seafloor, which means chemistry, minerals dissolving, hydrothermal vents possibly. The same kind of environment where life might have started on Earth. But here's the new part. In 2025, researchers analysing Juno's magnetometer data detected variations in Europa's induced magnetic field that suggest the ocean isn't just sitting there, it's active. There are currents, possibly convection cells, temperature gradients. The ocean is dynamic, which means energy is flowing through it, and where there's energy, there's potential for life. Ganymede is even more complex. It has its own intrinsic magnetic field, the only moon in the solar system with one. That field interacts with Jupiter's massive magnetosphere, creating a mini-magnetosphere around Ganymede itself. And beneath that magnetic shield, there's an ocean. Maybe multiple oceans stacked in layers between ice shells of different phases. The complexity is staggering. Callisto, the outermost of Jupiter's large moons, is quieter, less active. But even Callisto might have a subsurface ocean, hidden deep beneath an ancient cratered surface. And if Callisto, the least promising candidate, has liquid water, then the Jupiter system is even more habitable than we thought. All of this matters for 3I-ATLAS because the object is heading there. March 16th, 2026. 0.35 astronomical units from Jupiter. That puts it closer to Jupiter than many of the moons. It'll pass through the magnetosphere. It'll experience radiation. It'll be bathed in charged particles and electromagnetic fields. If the object is measuring magnetospheres, If it's sampling planetary environments, then Jupiter is the crown jewel. Jupiter's magnetosphere is the largest structure in the solar system outside the Sun itself. It extends millions of kilometers. It traps charged particles from the solar wind and from volcanic plumes on Io. It interacts with the moons, inducing currents in their oceans, creating auroras, shaping their environments. An object passing through could measure all of this: field strength, particle density, plasma composition, the interaction between the magnetosphere and the moons. If you wanted to understand how magnetospheres protect or expose subsurface oceans, if you wanted to know whether electromagnetic interactions could support life chemistry, Jupiter is where you'd go, and the timing is perfect. By March 2026, ESA's JUICE mission will be arriving at Jupiter. NASA's Europa Clipper will be on its way or already there. Juno will still be operational. The Jupiter system will be the most instrumented, most heavily observed location in the solar system outside Earth. Multiple spacecraft with magnetometers, spectrometers, cameras, radar, all watching, all measuring, and through that gauntlet of sensors 3I-ATLAS will pass. This is where the instrument hitchhiker hypothesis becomes really interesting. Because if the object is designed to be observed, if it's placing itself where our instruments can study it, then the Jupiter encounter is the main event. Everything before, Mars and Venus, those are warm-ups. Jupiter is where the data gets rich. Jupiter is where our capability meets the object's trajectory. But there's another angle. The magnetosphere studies show us that these environments are complex. They're not just empty space around planets. They're active, dynamic, filled with particles and fields and interactions we're only beginning to understand. If you wanted to hide something, if you wanted to deploy payloads or conduct measurements without being obvious, the magnetosphere is perfect. The background is noisy. The environment is chaotic. Small anomalies would be lost in the natural variability. A probe released into Jupiter's magnetosphere could drift for years, powered by the electromagnetic fields, gathering data on the moons as it passes them. It could position itself near Europa, watching for plumes, sampling particles if a plume erupts. It could orbit Ganymede, studying the interaction between the moon's magnetic field and Jupiter's. It could settle into a stable Lagrange point and just observe, and we'd never find it. Because Jupiter's environment is vast and our instruments are focused on the moons themselves. We're looking at Europa's surface, at Ganymede's interior, at Callisto's craters. We're not scanning empty space for small, silent objects that don't reflect much light and don't emit signals. The advances in magnetosphere science also tell us that these environments matter for habitability. Europa's ocean is kept liquid by tidal heating, but the magnetosphere plays a role too. Charged particles bombard the surface, breaking apart water ice, creating oxygen. Some of that oxygen might make it into the ocean. That's potential energy for life. That's an electron donor. That's chemistry. If someone is conducting a survey of habitable environments, they'd need to measure this. Remote sensing can't tell you about magnetosphere interactions. You need to be there. You need instruments in the environment, measuring field strength, particle flux, radiation dose. And if 3I-ATLAS is carrying those instruments, or if it's deploying smaller probes that carry them, then the Jupiter encounter is where that mission succeeds or fails. There's also the question of what the object experiences. Passing through Jupiter's magnetosphere at 0.35 AU means exposure to intense radiation. Jupiter's radiation belts are brutal. They're strong enough to fry electronics, strong enough to damage organic molecules. If 3I-ATLAS is a natural comet, that radiation will interact with its surface, processing the ice, creating chemistry. If it's artificial, the radiation is a challenge. Shielding becomes necessary, hardening, redundancy. How the object behaves during and after the Jupiter pass might tell us something. Does it maintain its trajectory? Does it show signs of damage? Does its outgassing pattern change? Any anomaly, any deviation from predicted behavior becomes significant. Because natural objects respond to radiation in predictable ways. Artificial objects, if they're well designed, would respond differently. They'd compensate, adapt, survive. We won't know for months. The Jupiter encounter is still ahead, but the infrastructure is being put in place. Juno is ready. JUICE is coming. Europa Clipper is coming. The instruments are warming up. The observation plans are being made. And when 3I-ATLAS arrives, we'll have the best view of an interstellar visitor interacting with a planetary environment that we've ever had. If there's a secret to be revealed, if there's a signature that proves this object is more than a comet, Jupiter is where we'll find it. Because Jupiter doesn't hide anything. Jupiter amplifies. Its magnetosphere is a magnifying glass, a natural laboratory where anything unusual stands out. And 3I-ATLAS is heading straight into it. The magnetosphere studies of 2025 have shown us that these environments are active, complex, and potentially habitable. They've shown us that electromagnetic interactions matter for life. They've shown us that the Jupiter system isn't just interesting, it's crucial. It's a nexus, a hub, a place where multiple habitable environments cluster around a single massive planet. If you were designing a survey route, if you were planning a trajectory for maximum data collection, Jupiter would be on the list. Not just to pass by, but to thread through the magnetosphere, to sample the environment, to measure the interactions. And that's exactly what 3I-ATLAS is doing. Coincidence? Maybe. But the coincidences are piling up. The trajectory, the chemistry, the timing, the instrumentation, each one individually explainable, all of them together, that's a pattern, and patterns mean something. Part 13, Breakthrough, Artificial Intelligence in Spacecraft Autonomy and Deep Space Monitoring. Something else happened in 2025 that's worth talking about. We got better at building autonomous spacecraft. A lot better. And that matters because if we're speculating about interstellar probes, about objects that travel between stars conducting surveys, then autonomy is the key technology. You can't have a human operator when the nearest star is light years away. You need systems that think for themselves. NASA and ESA both demonstrated advanced AI-driven spacecraft systems this year. Small probes with onboard decision-making, swarms of CubeSats that coordinate without ground control, deep learning algorithms that can identify targets, plan trajectories, and execute maneuvers without waiting for commands from Earth. This isn't science, fiction. This is operational technology being tested right now. One example is the Autonomous Asteroid Monitoring Network, a constellation of small satellites equipped with AI that can detect, track, and characterize near-Earth objects. The satellites decide what to observe, they adjust their instruments, they prioritize targets, they share data with each other, and they do all of this faster than any human-controlled system could. Another example is deep space exploration. The latest Mars rovers and orbiters have autonomous navigation. They can avoid hazards, choose routes, collect samples based on scientific criteria, all without waiting for the signal delay. Mars is light minutes away. Commands take 10 to 20 minutes to reach the surface. If you need to react quickly, you need autonomy. Now scale that up. Not light minutes, light years. An interstellar probe can't phone home for instructions. The round-trip signal time is measured in years or decades or centuries, so the probe has to be smart. It has to make decisions, identify targets, adjust trajectory, deploy payloads, gather data, store it, transmit it when possible, survive failures, adapt to environments. And here's the thing. If we're building systems like that now, with our current technology, then an advanced civilization millions or billions of years ahead of us could build something vastly more capable. Something that doesn't just follow programming but learns. Something that can improvise. Something that could arrive in a new star system, assess the environment, and decide what to do without any external guidance. That's what an interstellar probe would need to be. Not a passive instrument, not a pre-programmed sequence, but an intelligent system, an explorer, an autonomous agent. And if 3I-ATLAS is such a system, if it's more than a comet, then everything we've observed starts to make sense. The trajectory that threads the planetary corridor, autonomous navigation choosing an optimal path, the chemistry that matches the target environments, adaptive camouflage or purposeful composition. The timing that coincides with our observational capabilities, awareness of the system's infrastructure. An AI-driven probe wouldn't need to be large. It wouldn't need massive engines or huge instruments. It would be efficient, compact, self-repairing. It would use local resources, gathering materials from asteroids or planetary atmospheres. It would hibernate during the long interstellar journey, conserving energy. It would wake up when it detects a star system, assess, and act. We're also getting better at detecting anomalies. Machine learning algorithms are now used to analyze astronomical data, looking for patterns that humans might miss. Unusual light curves, unexpected spectral features, trajectory deviations. These algorithms have found exoplanets, identified supernovae, detected gravitational waves, and they're getting better every year. If someone wanted to hide an artificial object among natural ones, they'd need to account for this. They'd need to be subtle enough to evade machine learning detection, which means either perfect camouflage or intentional revelation. Either blend in so well that no algorithm can distinguish you from nature, or stand out in ways that look natural enough to be dismissed. 3I-ATLAS might be threading that needle, unusual enough to be interesting, normal enough to be explained, right on the edge of detectability. There's also the question of networks. Our AI systems are moving toward distributed intelligence, swarms, collectives, systems where multiple small units work together, sharing information, coordinating actions. No single unit is in charge. The intelligence emerges from interaction. If interstellar probes operate the same way, then 3I-ATLAS isn't alone. It's part of a network. Oumuamua was part of the network. Borisov was part of the network. Each one an independent agent, but all of them connected somehow, sharing data, coordinating, building a picture of the galaxy together. We can't detect that coordination. We can't see the communication. It might be happening at frequencies or through methods we don't monitor. Quantum entanglement, gravitational waves, neutrinos, something exotic. Or it might be happening slowly across years or decades, patient and methodical because there's no hurry when you're an immortal machine. The advances in spacecraft autonomy in 2025 show us that this is possible. We're doing it on a small scale. We're building systems that can think, explore, and adapt. And if we can do it with a few decades of computer science, then someone else, somewhere else, could do it perfectly. This is relevant because it changes how we think about detection. We've been looking for obvious signs, transmissions, artificial structures, anomalous accelerations. But an AI-driven probe wouldn't give obvious signs. It would be careful, methodical. It would observe without interfering. It would blend in. The only way to detect such a system is to look for subtle patterns, statistical improbabilities, trajectories that are too precise, chemistry that's too convenient, timing that's too perfect. And that's exactly what we're seeing with 3I-ATLAS. It's not proof, but it's suggestive. And in the absence of proof, suggestive is all we have. The AI breakthroughs of 2025 also point to another possibility. What if the probes aren't just gathering data? What if they're learning? What if each encounter with a planetary system updates their models, improves their strategies, refines their understanding? An AI that's been operating for millions of years, visiting thousands of star systems, would be incredibly sophisticated. It would know how to approach a system without causing alarm. It would know what to measure and where. It would know how to interpret the signs of life, technology, habitability. It would be an expert surveyor. And that's what 3I-ATLAS is, then we're being surveyed by something that knows exactly what it's doing. Something that's done this before, many times. And whatever conclusions it draws about us, whatever data it collects, will be added to a database that spans the galaxy. That's humbling. And a little terrifying, because it means we're not just being observed, we're being understood by something we don't understand at all. Part 14, Breakthrough, Solar System Interceptor Missions and Small Body Rapid Response. Here's a problem. We're good at detecting interstellar objects now. We have surveys running. We have algorithms watching for unusual trajectories. But detecting isn't enough. We need to intercept. We need to get close, take measurements, maybe even sample material, and we're not ready for that. In 2025, both NASA and ESA released proposals for rapid response interceptor missions. The idea is simple. When an interstellar object is detected, you launch a small, fast spacecraft to catch up with it. You don't need a big mission. You don't need years of planning. You need a spacecraft on standby, a launch vehicle ready, and a trajectory plan that can be calculated quickly. ESA's Comet interceptor mission is the prototype. It's designed to launch and then wait in space at a Lagrange point until a suitable target is identified. Once a target appears, the spacecraft leaves its parking orbit and intercepts. It doesn't need to rendezvous or orbit. It just flies past at high speed, taking measurements during the brief encounter. NASA is working on similar concepts. Small spacecraft with ion drives that can accelerate over months or years, building up enough velocity to catch an interstellar visitor, even after it's been detected on its way out. The technology exists. The challenge is readiness. And here's the frustration. We missed Oumuamua. By the time we realized what it was already leaving. We got a few measurements, but nothing detailed. No close-up images, no in situ analysis. It's gone now, beyond the reach of any mission we could launch. We did better with Borisov. We had more time, we took more data, but we still didn't intercept. We watched from a distance, and now 3I-ATLAS. We're watching in real time. We know where it is, we know where it's going, but we're not sending anything to meet it. Not yet, because interceptor missions take time to plan, fund, build, launch, and by the time we're ready, the object will be gone. That's the gap, that's the vulnerability. We can see these objects, but we can't touch them. And if they're hiding secrets, if they're more than they appear, we're not going to find out by staring from Earth. The breakthrough is that we're finally taking this seriously. The rapid response programs are being funded. The technology is being developed. By the time the next interstellar object arrives, we might be ready. We might have a spacecraft, waiting. We might be able to launch within weeks instead of years. But that raises a different question. If we're preparing to intercept the next visitor, are they aware? If 3I-ATLAS is part of a surveillance network, does it know we're building interceptors? Does it care? Maybe that's part of the test. Maybe the survey isn't just measuring our current capabilities, but our trajectory. How quickly we improve. How long it takes us to go from detection to interception. Whether we're reactive or proactive. If that's the case, then our response to these objects is itself data, and whoever sent them is watching how we react. There's another angle. Interception capability is also defense capability. A spacecraft that can intercept a comet can intercept a missile. A network that can track small bodies can track military assets. The technology is dual use, and if we're developing it, we're signaling something. We're saying, we see you, we can reach you, we're not passive. That might change the calculus. If the probes are assessing threat levels, if they're measuring whether a technological civilization is dangerous or benign, then our ability to intercept becomes significant. It's a line we're crossing, from observation to action, from passive to active. And maybe that's when things change. Maybe that's when the next phase begins. Because if we can intercept, if we can touch these objects, then we can learn what they really are. We can settle the question, natural or artificial, random or designed, coincidence or intention. The interceptor missions of 2025 and 2026 are humanity's first serious attempt to close the gap, to go from watching to reaching. And when that happens, when we finally catch one of these visitors and bring back data that's not filtered through millions of kilometers of space, we'll know. We'll know if the galaxy is empty or full. We'll know if we're alone or observed. We'll know if these objects are messengers or scouts or something else entirely. Until then, we watch, we wait, and we build our interceptors, because the next visitor is coming, and this time we're going to be ready. Part 15. Final synthesis and outlook. What it all means for us. Let's bring this home. Let's talk about what all of this means, not for science, not for astronomy, but for us, for humanity, for the way we see ourselves in the universe. 3I-ATLAS entered our solar system on July 1st, 2025. It's threading a path through the planetary corridor, passing Mars, approaching Venus, heading for Jupiter. Its trajectory is precise, its chemistry is unusual, its timing is convenient. And taken together, all of these facts weave a narrative that's hard to ignore. The mainstream scientific view is clear. This is a comet, an interstellar comet with unusual but explainable properties, hyperbolic orbit from another star system, CO2-rich composition from formation, environment or cosmic ray processing, retrograde trajectory that happens to be nearly coplanar, statistical coincidence, natural variability. That's the safe interpretation. That's the one that doesn't require extraordinary claims. And extraordinary claims require extraordinary evidence. Right now, the evidence is circumstantial, suggestive but not definitive, interesting but not conclusive. But, there's always a but. The trajectory threads 3 worlds that represent 3 stages of habitability. The chemistry matches those worlds. The timing coincides with maximum observational coverage. The statistical probability is low but non-zero. And every new data point, every new measurement, seems to add another layer to the pattern. If this were the only interstellar object, you could dismiss it. But it's not. Oumuamua was different. Borisov was different. Atlas is different. 3 objects, 3 chemistries, 3 trajectories. And if you're looking for a pattern, the pattern is diversity. Purposeful diversity. The speculative hypotheses we've explored, instrument hitchhiker, resource harvester, reconnaissance probe, Trojan horse payload, they're not proven. They're possibilities, thought experiments, ways of asking what if. But what if is where all discovery starts. What if the Earth orbits the Sun? What if germs cause disease? What if the universe is expanding? What if we're not alone? And what if 3I-ATLAS is more than a comet? That question has implications. If it's artificial, if it's part of a survey network, then the galaxy is being watched, mapped, catalogued by something old, something patient, something that operates on timescales we can barely comprehend. If that's true, then Earth is already in the database. We've been measured, our atmosphere analysed, our biosphere catalogued, our technology noted, and whatever system is collecting this data has a file on us. Homo sapiens, technological species, third planet, active. That should change how we think about ourselves. We're not isolated. We're not undiscovered. We're part of a larger context, a galactic ecosystem. And whether we like it or not, we've been noticed. But here's the thing. Being noticed isn't the same as being contacted. 3I-ATLAS isn't slowing down. It's not broadcasting. It's not trying to communicate. It's passing through, taking measurements, moving on. We're just one stop on a very long journey. And maybe that's the most unsettling part. Not that we're being watched, but that we're not that interesting. We're a data point, a sample, a single entry in a catalogue that includes thousands or millions of other worlds. We're not special. We're not central. We're just another inhabited planet in a galaxy that might be full of them. That's the Copernican principle taken to its logical conclusion. Earth isn't the centre. The Sun isn't the centre. Our galaxy isn't the centre. And maybe our existence isn't particularly noteworthy either. We've spent centuries moving, ourselves from the middle of everything to the edge of everything, from the centre of creation to a pale blue dot orbiting an average star in an average galaxy. And now, maybe, we're just another entry in someone else's spreadsheet. But there's another interpretation. Maybe we're being left alone deliberately. Maybe there's a protocol, a rule. Don't interfere with developing civilizations. Let them grow. Let them figure things out. Watch from a distance, but don't engage. Not yet. The corridor threading, the Earth avoidance, the subtle passage through instrumented zones, all of it could be careful non-interference. A way of observing without disrupting. A way of gathering data without changing the outcome. Scientists on Earth follow protocols when studying endangered species. You observe without interfering. You take measurements without changing behaviour. You document without disrupting. Maybe whoever sent these objects follows similar rules. Maybe there's a galactic ethic that says, let them develop naturally. Don't contaminate the experiment. If that's the case, then the question is, when does the non-interference end? When do we cross the threshold from observed to acknowledged? Is there a line, a technological milestone, a behaviour? And if we cross it, what happens? Maybe the line is interstellar travel. Maybe when we can reach other star systems ourselves, when we become part of the interstellar community rather than just inhabitants of a single planet, that's when contact happens. Maybe they're waiting for us to join them rather than coming to us. Or maybe the line is something else. Maybe it's about how we treat each other, how we manage our planet, whether we survive our technological adolescence. There's a concept in astrobiology called the Great Filter. The idea that somewhere between single-celled life and galaxy-spanning civilization, there's a barrier. Something that most species don't survive. Climate collapse, nuclear war, artificial intelligence gone wrong, engineered pandemics. Maybe the survey is checking which civilizations make it past the filter and which ones don't. And if we're being catalogued, if our status is being updated regularly, then maybe the next update depends on what we do now. Do we solve climate change or let it spiral? Do we manage our technology wisely or destroy ourselves with it? Do we unite as a species or fragment into conflict? These aren't just questions for us. They might be data points for whoever's watching. We don't know. We can't know. Not without more data. And the data is coming. The Venus pass is imminent or recent, depending on when you're reading this. The Jupiter encounter is months away. Every telescope we can point at this object is watching. Every spacecraft in the corridor is ready. And maybe this time we'll find the anomaly, the signature, the thing that proves it's not just a comet. Or maybe we won't. Maybe it'll pass through, behaving exactly as a natural object should, and we'll be left with our speculations and our questions. Either way, the conversation has changed. We're no longer asking if interstellar objects exist. We know they do. We're asking what they are, what they mean, whether they're messengers or scouts or samples or something we don't have words for yet. And that's progress. That's humanity doing what humanity does best. Looking at the universe and asking why. Seeing patterns and wondering whether they mean something. Taking data and spinning it into stories that might be true. The scientific method demands skepticism. It demands that we don't jump to conclusions, that we gather evidence, that we test hypotheses, that we remain open to being wrong. And that's good. That's how we avoid falling into superstition and pseudoscience. But skepticism shouldn't become blindness. Being careful about conclusions doesn't mean refusing to see patterns, and the pattern here, whether natural or artificial, is worth examining. Because here's what we know for certain. Interstellar objects exist. They pass through our solar system. They come from other star systems, places where different suns shine and different worlds orbit. Each one is a sample of somewhere else, a piece of another neighbourhood delivered to our doorstep, and whether they're natural debris or designed probes, they're valuable. They're windows into the wider galaxy. The terrifying truth isn't that 3I-ATLAS is coming for us, it's that it doesn't need to. We were already measured, already catalogued, already classified. Earth is just one data point in an automated census of life that's been running for longer than our species has existed. Somewhere in the dark, an ancient system is updating its records, noting which worlds still breathe and which ones have gone silent. And we're in that database now. Active, inhabited, technological. Status, ongoing. Think about that. Status, ongoing. Not complete, not finished. Ongoing. We're still happening. Still evolving, still developing. And whoever or whatever is keeping those records is patient enough to watch how we turn out. Whether we thrive or collapse. Whether we reach for the stars or turn inward and fade. That's both humbling and empowering. Humbling because it means we're not as important as we thought. The universe doesn't revolve around us. We're not the main event. But empowering because it means we still have agency. Our story isn't written yet. The outcome isn't predetermined. What we do matters, even if it only matters as one data point among billions. What happens next is up to us. We can ignore it. Dismiss the pattern as coincidence. Go back to thinking we're alone. That's the comfortable option, the safe option. It doesn't require us to change anything about how we see ourselves or our place in the cosmos. Or we can take it seriously. We can prepare. We can build our interceptors. We can watch more carefully. We can ask better questions. We can operate under the assumption that we might be observed and act accordingly. Not paranoid, not fearful, but aware. Thoughtful. Intentional about what we're doing and what signals we're sending. Because if we are being watched, if these objects are part of a survey, then everything we do is visible. Our wars, our accomplishments, our treatment of our planet, our attempts to reach beyond it. All of it is data. All of it is being recorded, and maybe, just maybe, all of it is being judged. That's not meant to be scary. It's meant to be clarifying. If we're part of something larger, if we're being catalogued as part of a galactic ecosystem, then our responsibilities extend beyond ourselves. We're not just stewards of Earth, we're representatives of Earth, ambassadors whether we intended to be or not. And that changes things. It gives our actions cosmic significance. Not because we're special, but because we're being observed. Because somewhere, someone or something is keeping track. Noting what we do, recording how we handle the challenges we face. We're living in the moment when this becomes real, when interstellar objects go from theoretical possibilities to observed realities, when the question of whether we're alone transitions from philosophy to data analysis, when the galaxy stops being a distant abstraction and becomes immediate, tangible, present, because the objects keep coming, and every one of them is an opportunity to learn, to discover, to maybe finally confirm that the universe is bigger and stranger and more alive than we ever imagined. 3I-ATLAS will leave, it'll accelerate back into interstellar space, it'll fade from our telescopes, and eventually we'll lose track of it. The coma will dissipate, the trajectory will carry it beyond our detection range. It'll become a ghost, a memory, a footnote in astronomical databases. But it's not the end, it's the beginning. Because now we know what to look for. Now we know the pattern. We know that interstellar visitors thread through our system on trajectories that sometimes, maybe more than sometimes, look purposeful. We know they come in different varieties, different chemistries, different behaviours. We know they pass worlds of astrobiological interest. And we know they do it with a frequency that suggests they're not as rare as we once thought. And when the next visitor arrives, when the next interstellar object threads through our system with impossible precision, we'll be ready. We'll be watching. And maybe this time we'll get close enough to see what it really is. Maybe this time we'll have our interceptors in place. Maybe this time we'll be able to sample material directly, to take high-resolution images, to detect anything artificial if it's there to be detected. Or maybe we'll confirm it's natural. Maybe we'll find that the universe is just strange and random and full of coincidences, and that would be okay too. That would be valuable. Because either answer, artificial or natural, tells us something profound about the galaxy we live in. Until then, we wait, we watch the sky, and we wonder whether somewhere out there something is watching us back, quietly cataloguing, patiently recording, updating files in a database that spans the galaxy, and maybe, just maybe, wondering if we'll ever figure it out, wondering if we'll notice the pattern, wondering if we'll understand what it means, wondering if, when we finally do, we'll be ready for the implications. The universe is speaking. It's been speaking all along, through objects that pass in the night, through trajectories that don't quite make sense, through chemistry that's just unusual enough to make you think. And now, finally, we're learning to listen. What we hear might change everything, or it might change nothing. But either way, we're listening, and that in itself is progress. That's humanity reaching beyond itself, asking questions that matter, looking for answers in the only place they can be found, out there in the darkness, where the visitors come from. The story of 3I-ATLAS isn't over. It's just beginning, and we're all part of it now, whether we realise it or not. Every person who looks up at the night sky, every scientist who analyses the data, every person who wonders what it means. We're all witnesses to something that might be the most important discovery in human history. Or it might just be a comet. Either way, it's worth paying attention. Because the universe doesn't give us many chances to see beyond our own small corner of space. And when it does, when it sends us visitors from other star systems, we owe it to ourselves to look carefully, to think deeply, to wonder honestly. That's what 3I-ATLAS has given us. Not answers. Questions. Better questions. More profound questions. Questions that might eventually lead us to understand our place in a universe that's far more complex and interconnected than we ever imagined. And that's worth celebrating. That's worth pursuing. That's worth staying awake for.